Hello, welcome back to the Chapter 6.4 video lecture series. In the last video, we were looking at a confidence interval example. We're looking at 210 total first-year college students, where 78 were assigned to a room with a roommate who had a video game system. And after the first semester, we got an average GPA with standard deviation. And then the other part of that sample, 132 students were assigned to roommates who did not have a video game system. Slightly higher average GPA with the standard deviation. So we were starting to go through how to calculate a 90% confidence interval. So here's what we had so far. I just condensed that information into our sample statistic variables here for the video game group, the non-video game group, and then how to create a confidence interval. Noted we only know the sample data. We don't know anything about population standard deviation, and sample sizes are both 30 or more, so we can use t-star. Degrees of freedom are the smaller of the two sample sizes minus 1, so 77. Our formula for the confidence interval is the difference of the two sample means plus or minus t-star times the standard error. And we're finished the last video as I was going through the standard error formula is the sample standard deviation squared over each sample size. Add them together, and then take the square root. So as a formula, this would be 0.625 squared divided by the sample size for the non-video game group was 132. And then we're going to add, the other group had a sample size 78. Video game group, and their standard deviation was 0.669. And then we're going to square that. All right, so I threw that in my calculator. Don't forget you want to square, divide, and add before you take the square root. And let me double check. I got that to be about 0.09325. So 0.093 for my standard error. All right, so I want to get t-star next. I got standard error, t-star. I'm going to go to stat key. All right, I got stat key here. For t-star, we're going to go to the theoretical student t distribution. It's going to ask you for degrees of freedom, which I already noted before is 77 in this example. Click on two-tail. And we want a 90% confidence interval. So back to stat key. Two-tail, make sure that middle error area entry says 0.90. Got 0.90. So t is going to be 1.665. We could use either value since we're doing the plus or minus, but I'll use the positive, t 1.665. So t star is 1.665. So then the confidence interval is going to be the difference of the two means, so 3.105 minus 2.84. Plus or minus t star 1.665, and then times standard error 0.093. So putting that together, let's do the 3.105 minus 2.84 is going to be 0.265 plus or minus 1.665 times 0.093. And that ends up being about 0.155. 0.155. I go to 3 decimals. So the confidence interval is going to be, I'll do interval notation. If I subtract 0.265 minus that value, I get 0.1101. And then if I add 0.265 to 0.155, I get 0.42. So right here, and all said and done, I'm just going to highlight this. There we go. There's my confidence interval and interpretation. We are 90% confident that, what is this saying? So notice here I did non-video game minus video game. So people without video games did a little bit higher. So that students who do not have a video game system in their room have a GPA between 0.11 and 0.42 higher than students who do not have a video game system in their room. And there's more caveats here. We're only looking at the first semester of freshmen, so it might have more to do with being away from college, and maybe there's not a longer term effect. But this is a nice little interpretation, given that assumption that we're just looking at the first semester with this data. All right. Okay, so on the next slide, kind of going through all the same steps. I'll go through this a little bit faster. The conditions were met. We have at least sample sizes of 30. T star, we got T is 977 degrees of freedom. So going into stat key, we get that T star to be 1.665. The statistic is the difference of those two sample means. Ooh, so on the slides, I did the reverse order. I did video games minus non-video games. Standard error, we calculate that to be 0.093. And confidence interval, notice here, because when I created these slides, I did the two groups the opposite, we ended up with negative 0.42 to negative 0.11. So that would be appropriate. If this were, a quiz or exam question, I would accept both of these. The only thing different is how I switch the two groups. So both are appropriate. But the interpretation is going to be the same. We're 9% confident that getting assigned a roommate who brings a video game system to college decreases the mean GPA by these two values. So the wording is slightly different, but the context, the setup's still the same. It's better to not have a video game system for your GPA, at least in the first semester of college. All right, let's look at doing hypothesis test. So t-test for difference of means. We're always in this class going to assume the averages are the same. Our test statistic is going to be your statistic minus the null over the standard error. So in this case, that's given here. Again, this is going to be on your formula handout. T is the difference of the two sample means divided by that standard error formula. And as before, we need to assume the populations are normally distributed, or we're safe as long as the sample sizes are big enough, at least 30. They both have to be at least 30. And the p-value is going to be computed as the area of the tails beyond the t of a t-distribution, and we're going to use the same degrees of freedom. The smaller of n1 minus 1 and n2 minus 1. All right, so I've got one example to look at, one hypothesis test. And this is called the Pygmalion effect. And that's the greater the expectation placed upon people, the better they perform. There's been multiple experiments done in this, both in education, also in business, psychology, etc. But teachers were told that certain children, chosen randomly, were expected to be growth spurters based on the Harvard test of inflection acquisition. This is a fake test. And this experiment was done a while ago. This is one of the earlier psychological tests done on this Pygmalion effect. And the response variables change in IQ over the course of 1 year. And sometimes we think about IQ as being fixed. It is not. I think most people have a confidence interval, if you will, of IQ, and then it's their life decisions, how you think and challenge yourself and whatnot. Could definitely change your IQ. So the idea is one group was told nothing, and the one group was randomly told you're going to be growth spurters, your IQ is going to grow, and just to see if that would do it. Otherwise, the students were all in the same classes and whatnot. And here's the data summary. The control students were not told that they were growth spurters. Much bigger sample size, but that's okay. X bar is their average increase in IQ over the year. So this is an increase. And their standard deviation is 12. And then there's a 65, the experimental group that were told that they were growth spurters. Their sample size is 60. Their sample mean is 12.22. And standard deviation is 13.3. So notice these growth spurters had an increase, a larger growth of IQ over the year. The question is, though, is this big enough considering the standard error, standard deviations, and sample size? Can we generalize this to all all students, all people? All right, so does provide evidence that the Pygmalion effect exists, that expecting a child to do better actually causes the child to do better? All right, so what if we take this down one by one? What are the hypotheses? We're going to always assume the two population means are equal. And here in this case, mu1 is equal to the average change in IQ for the growth spurters. Students that were told that their IQ is expected to grow. And, oh, another typo. Let me fix that. Sorry about that. So we have two groups here. Second group is the mu2 is the average change in IQ for control group, for the control, the students that were not told that there would be growth spurters. So we want to test, we'll go back. Sorry. Does this provide evidence that the Pygmalion effect exists, that expecting a child to grow actually causes the child to be better? So that alternative hypothesis, we're going to assume that the average change in growth is greater for the growth spurter group. All right, conditions. Sample size for 1 was 65 for the growth spurters, definitely bigger than 30. And the second sample size, the control group, was 255. So we're good there. We check conditions. Sample sizes are large enough to use t distribution. So calculating the statistics, the difference in the two sample means, is the 12.22 minus 8.42 to get 3.8. The standard error formula says to take standard error, the square root of s1 squared over n1 plus s2 squared over n2. So we're taking the two sample standard deviations over the sample sizes. Notice here the sample sizes are not the same, but that's perfectly fine. The main issue is that they're both at least 30. And the 65 group, their standard deviation was 13.3. So you got to make sure you put these over the correct fraction. Throw that in your calculator to get 1.813 as your standard error. And it'd be worth making sure to throw this in your calculator. Make sure you're getting the same thing as I'm showing here on the slides. It's 1.81275. So round that to 3 decimals. The test statistic, instead of z, we're going to use t. My test statistic is your statistic, which I have up here, 3.8, minus the null. And I could put a 3.8 minus 0 right here. The null we're assuming to be 0, 0 difference of means, divided by the standard error. And we get that to be 2.09625, so 2.096. All right, and compute p-value. I have it on the slides, but if I have got my test statistic, I'm going to go back here. Before I go to that, we're going to use t with 65 minus 1, or 64 degrees of freedom. Remember, we're going to use the smaller of the two sample sizes, minus 1, and that'll be 64. So if I go back to stat key, that t distribution, we're going to take 65 minus 1, so 64 degrees of freedom, and the test statistic, we want to see how far is that test statistic, 2.096, how far is that from 0? And I was going to assume 0 is the null hypothesis for difference of means. So I'm going to click right tail and enter down here. Don't forget, you do need to change this. Once you click right tail, it's always going to say 0.025. So So you have to change that bottom entry to 2.0.